know about the MATLAB. This is a new technique, and it is very good time for you to learn. You have to, if you look at compared to us, you have a long time to practice this software. You can use it in your you can say teaching assignments or your research. Okay, so my purpose is that everybody over here, he must start using the MATLAB, maybe for a very, very basic problem. So once you get interested, then no problem. You have a code with you, you have a software with you. We can arrange that software from the computer science department, because this is the university has purchased the MATLAB, so it can be downloaded to other, or it can be uploaded to the other computer also. Okay, so let us hope so that by the end of this course, everybody should start using the MATLAB. At least he should practice he should solve one problem. So I request Dr. Donald to kindly manage the things in such a way that today at 2:30 to 4:30 we have one tutorial. In that I told him that we need not to discuss too much theory, but let whatever he has taught to you regarding the MATLAB, so you practice that, you solve some problem, you plot some graphs, especially surface graphs, which is very good in that. So he will be helping us. So let us hope so that we may start using this program in time to come. All people become expert in that. Okay, good luck. Please, Dr. Donald, please.
Okay, thank you, Dr. Sogi. So I created another new code today per Dr. Sogi's request. He wanted me to do a code that would analyze the rheology data. So I created some rheology data this morning, put it together, and I will get all the codes loaded after lunch, okay, when I get back to the guest house. So it should be all uploaded by 1:30, okay? So just go to the Google Drive and look for the folder that says MATLAB codes, and just copy the whole folder so you have it onto flash drive or your phone or whatever is good for you. And then I'll meet you in the afternoon, and we'll just go through it. And you just watch what I do. I'll do it slowly, same thing I'm doing now, and you click through it and do the same thing. I just want you to get used to it. So this morning, these two lectures, I want to do really just something on, I want to teach you the ODE 4.5 solver for differential equation. It's not that difficult. I will show you how to do it. Then I will show you an example, how to solve a differential equation, ordinary differential equation. That'll be the first lecture. In the second lecture, I'm going to go through my code cell by cell. Remember I said cell means a paragraph. So I'll go through paragraph by paragraph, and you will see how I set up my system. You remember yesterday I showed you my step 1, step 2, step 3. My code has step 1, step 2, step 3, and you'll see the code solving a problem with the data, with the mathematical model. You'll see how to do it, and then in the afternoon we'll do it. Okay? So my hope, what I want when I leave India and you go back to your studies, I hope that you can be able to use two things. One is the CF tool, the curve fitting tool. Remember I showed you that? So we'll do that this afternoon. If you can use the curve fit tool, that's a GUI, graphical user interface. And then the number two is, I hope that you can use the codes I show you today. I have a template, and I hope that you can take that code, and then when you want to use your data, you just write your own function. You keep my code, you write your own function and your own data, and you put it into the same code. And the code only needs a very few changes, just a change in name, that's it. But you can keep the code as is. So in summary, if I can give you the curve fit tool and my code template, then I consider my visit to be successful, because you will be improved your research, okay? Just those two things out of the whole week, that's good enough, okay? All right. So now I will do the differential equation. It's not difficult, so stick with me. So let me do here we go. So let's talk about the setup, the syntax. Syntax is like this. Yeah, so here's a function, and if you had the derivative for this and you tried to solve it, you would have some problems because they say it's stiff. What do they mean by stiff? They mean on one part it's moving slowly, and another part it's moving fast. Slowly and then fast and slowly. So the problem is right here. The derivative is changing very rapidly, right? It goes up there and then it changes very rapidly. But here it's changing slowly. So that's a problem. So how does they solve it? So the Runge-Kutta method, what they do is, there are two ways to solve this. One is you can take your step size and cut it in half, cut it in half, cut it in half, like that. And every time you cut it in half, you solve it again and compare it to the previous. And then if the comparison is very close within a tolerance, then you stop and you say, I solved it. Okay, the other way is the Runge-Kutta method. And the Runge-Kutta method, what they do is, you take the Runge-Kutta fourth order method and you run the solution, and then it runs the Runge-Kutta fifth order method, and you compare the solution. And you keep doing that until the two solutions are not different. They're within a tolerance. So the reason is that the Runge-Kutta higher order is more accurate. So if you run the fourth order and then you run the fifth order and the difference is very small, then you can stop and you solved it, okay? So that's why we have these methods in MATLAB. So you have an ODE 2-3, and that means they use the second order and the third order. And then 4-5. So I'm going to do 4-5. So the 4-5 method means they run the Runge-Kutta fourth order and the fifth order, which is more accurate. They compare the two, and when the difference is small, they stop. So we're going to use the ODE 4-5. Solves the ordinary differential equation, fourth order, then fifth order. Now, yeah, and you should be happy because it's 2017. Back in 1950s, people had to do this by hand. Okay? For us, MATLAB does it for you. I'm just telling you the theory, okay? So here's how you do it. There are only three things that you have to give. So on the left side, you put your time and your y. Okay? Remember, what are we doing? You have a differential equation. It says dy dt equals something. So you know what the derivative is, but you don't know what the function y is. You want to solve for the y. Okay, that's what we want. So you put the t and the y is the solution on the left side, that's your output. On the right side, you put ODE 4-5, and you give three things. The first thing is the function. So that's going to give you the y values. Okay, so you have to give a function like dy dt equals minus ky. Okay, you have to write that in, and I'll show you how to do it. The t-span is simply the time, like from 0 to 10. So you have to put in 0 to 10. The y0 is the initial value of your function. So when you solve an initial value problem, you have to start on the left side and you have to give the initial value. You start from the left side and then you shoot the derivative forward and you move and get a value, and you shoot another derivative, get another one. So you're always moving from the left side to the right as the function moves. So you have to tell the function your initial value at time 0 equals 2 or 0, whatever it is. So that's it. Now, the t-span, there are two ways to do the t-span. So on the t-span, the first way is you put in two values, okay, and the ODE 45 automatically cuts it up into small pieces. And you can't control the pieces. It just goes, if you say 0 to 10, it may give you 100 steps. It's automatic. The second way is, if you want to have every time step specifically, then you put it in. So if you say, I want to have 0 to 100 and I want it at every one, then you just put 0 to 100 and give it more than 2 numbers. So you have to give it the entire vector, and then it will give you the answers at every point. So those are the 2 ways. Okay. And then the T-span, it has to either go up or go down. You can't make it go up and then down. It has to be strictly increasing or decreasing. And then the function looks like this. So I will show you how to write the function. You just put dy dt equals the function. Okay? And now I'll give you an example, right? So here's how it works. So I just chose something very simple. So we're going to say dy dt. By the way, these are just exponential decay. Everybody works with exponential decay. Food science, you do exponential decay of your nutrient in the food, or your color, whatever it is. But this is exponential decay. So you put dy dt equals minus 0.1 y. So that's going to be going down like this. And the rate is going to be minus 0.1. And you go from 0 to 10. So what do? First of all, now remember, I'm doing this very simple, so I can put it in the command window. When we get a little bit more complicated, we will write a function. But just for now, let's just put everything in the command window. Very simple. So by the way, anytime you see the and sign, you see that F1 equals and. The and tells MATLAB that it's a function. And then you write the ODE 45. Okay, when you write it, you have to put all 3 things in. So you have ty equals ODE 45, and then you put in F1 is the function, and then you put in your T-span. So the T-span is 0 to 10. So that means it automatically chooses how to cut it up. And the last thing is 1. So I put in 1 because it means at time 0. Right, so when you do differential equations, the function is unknown, or let's say again, when you do an initial value problem, the function is unknown except for 1 point. So, because if you do not specify the initial point, you end up with an infinite set of solutions, because the solutions will all look like this, but they'll start at different values, like start at 1, 0.8, 0.6, but the solution is the same except for the initial value. So you always have to give an initial value. Does that answer your question? Yeah. Everything. Okay, so I put my function into the command window. Everybody sees right here, F1 opens in the workspace, right? And you can see right there, right? So that's first thing. Next. Okay, now I want to solve it, right? So I have my function. All I want to do is solve it. And I paste it in. Solved. Now, how do I know it's solved? Well, look at the y. I have 41 values of y. You see all the values? Those are all my y's. And then I have all my t's. The t's were chosen by MATLAB. I did not choose them. I only chose the beginning and the end. MATLAB chose 41 values inside. Okay? Well, the only thing left to do is to plot it. So I'm going to plot it. I'm going to put a title and a label. wait a minute. I need to close. If you want to close, I need to close all my windows, all my plots first. So close all. Now I'm going to plot. There you go. So I have a title right here. I put my title. I have my Y. I have my time, and I plotted it. So here is the function. The function says the derivative is always minus 0.1 times y. So what you do is, my question was a little tricky because you don't know, is minus 1 right there, minus 1. Okay? It's as simple as that. Questions? Comments? Okay. So that's the first one. Now I'll take one little step forward. Next problem. I have a new function. My new function is y derivative dy dt equals sine of ty. Okay? So that means the derivative is always equal to sine of time times y. So I make my function. I write it there. Then I solve. Now, when I solve, I say, okay, I put in my function. I'm going from 0 to 10, and I'm starting at the point 1. So everybody sees the ODE 45, right? And then I plot it, hold on, and then that's title, and so on. Okay? So questions on that. You see the setup? So by the way, everything is loaded on Google Drive. These slides are on Google Drive. Okay? Okay, so let's paste it in. Close this. So I don't have a double space. Okay, now I paste it in. That's my new function. It's okay, you can clear. Let's try again. Okay. So I choose my arrow key and I can just bring up my history, right? And then I click on that. Oops. Okay, there's my function. The original function was like this. This new function goes like this. So it needs more points to get a good solution. That's why you have 93 instead of 41. All right? And then we do plot and title and so on. Okay, there you go. That's the solution. Now, let's look at the solution. It starts at 1, goes up, and then hits a peak and comes down like this. Now, let's go back to my chart here. Yeah, I want to show you how to do it with a function file. Okay, same solution, but we're going to do it with a file because that's normally how you do it. So let's do the function. I call it F2. So let's go to MATLAB. Now how do I do it? Well, look at this. I put an at right here. So it tells MATLAB it's a function, and everything else is the same. And then what it does is it goes and looks for a file. So let's go to MATLAB, and let's close this, move it over so you can see. I want you to see over here. Okay, so how do we do that? I'm teaching you how to do this. So we do new function. Okay, new function. And you can use this, or you can just paste in from my file. That's okay. So here's the function right here. I'm going to copy this in. All right, go to MATLAB, and let's copy it in here. So function dy, because derivative, right? Dy equals F2, and what is it? It's dy equals sine of ty. So I'm going to call that. Looking for the save, that's why. Okay, I can't find the save. Hang on. Here it is. Okay. Save as F2. Save. Now look over here. There it is, right? Everybody sees F2 sitting there. Okay, so now we have a file called F2. All right. So now I go back here. Let's move that. All right. So I'm going to call the file. And let's do this. Okay. I'm just going to call up my history. I just click on my arrow key on the computer. When you do the arrow, it shows everything that you've done recently. So now I'm going to bring this one up, but I need to change it like that, at F2. Everybody saw that? So I put at F2, 0 to 10, and 1, OD45. It should be ready to go. So now MATLAB, you notice before I had this. I had F1. When you don't have an at, it looks in the command window, or sorry, it looks in the workspace. So now it looks in the workspace. If I change it and go like this, at, then it looks for a file. Okay, that's the difference. So now let's run it. Okay, and I'm just closing all my plots. So we run it, and let's see what we get. So now I'm going to plot. Okay, same plot. But I look at this and I say, I don't like these numbers. They're very small and very difficult to read. So I want to increase the size. So you use a command that I have in my notes where you set the, you increase the size and you make it bold. So you can just copy that in. And now the figure, you see the letter, you see the numbers, they're much bigger and bolder. Okay, so it looks better. I could even change this line too. But let's keep going. Back to my, okay. Okay, let's do the label. So I need to put labels on it. What happened to my plot? It's strange. Okay, so I have Y and I have time. Okay, that's fairly straightforward, right? Simple. Okay, let's keep going now. See the plot. Now, can you help me here? Where is the derivative equal to 0? Approximately. Where do you see? Which one? At the, you said beginning? Where? Oh, at the peak. At the peak. Does everybody see the peak right here? You see that? So derivative is 0. You agree? Right? Derivative is 0 at that point. Well, we know what the equation is for the derivative. So, but I can only say, well, it's at the peak. But where is the peak? So here's how you do it. So you put in this, you put in this maximum. In other words, the peak means maximum. So we put in the maximum. And what do you get? Well, when you put maximum of Y, you get the C, and the C is telling you the value of the peak. So the peak is 1.92, and the I is telling you the index. In other words, it's going to be the y, the 10th value of y, and the 10th value of x. That's where the peak is. So let's show you the plot again. So you see 1.92 right here. And it's going to be at the 10th value of x and the 10th value of y. Well, so I have an I of 10, so let's do t of I and y of I. Okay? So t of I is 1.68. That's the time. And y of I is 1.92. Now the derivative is what? The derivative is the sign of the product. So I need to multiply the two together if I want to know, if I want to check. I want to see if my derivative, is my solution correct? I can double check. The solution says that the derivative at the peak should be 0. The peak is, you have to multiply the two together. So let's do that. All right, so I will do product equals, well, I'll just call it x peak. How's that? X peak equals t of I times y of I. Okay, it's 3.24. So if I do check, if this said minus 10, obviously my solution is wrong. Does everybody see that? Because the solution says that the peak has to have 0 derivative, okay? So that's a very helpful function. And I showed you this function yesterday when we did the surface. Remember we did your surface and I said maximum? And it's the same thing. Okay. The rest of these are probably, we don't need to get into these because they're just more complicated, and I want to show you some other things. Okay, so let's go to I think we did some of this, but I need to check. So, okay, we already did this, right? You've already seen, it's very similar, same idea. Same thing here. Okay, it's the same thing I just showed you. This is just more complicated. We don't need to do this one because I'm going to be busy on other things. You can do multiple equations, but we don't have time for this. Okay. Let's see. That's fine. Okay. Well, yeah. So I want to do something else. I want to get to this one to help you with your data. Okay, so that I already showed you now ODE 45. I think you know how to use it, right? And we'll practice this afternoon. So I want to get into finish off the inverse problem, because what I just showed you was a full mean the sensitivity coefficient. Okay, so let me pop that back up. So you have your small x and your y observed. That means you have your x observed and your y observed. Then you have your function on the right side, and then finally you have your guesses of your betas. Your betas are your parameters. For example, in the rheology, your parameters would be k and your n. I can make it up, and we have another model. I mean, not another, but you have just more complicated. So now we have 3 parameters. So my hope is it's this afternoon we will do option 2. So option 1 is very simple, just 2 parameters. Option 2 is more complicated because you're going to have, you usually run your experiment at 3 different temperatures. So what I did is I put everything together into one equation, and now you have beta 1 is Kref, beta 2 is, this is your beta T, and number 3 is your N. So you have 3 parameters. Okay, we'll do that this afternoon. Hopefully, I have it. I just finished it up. Okay, so those are your betas up there. That beta 0, you have to put in a guess because it's nonlinear, so you have to iterate. Okay, let's keep going. So notice, the NLin fit calls the forward problem multiple times, so we have to nest the forward problem. You put the calling statement and the function together inside another function. And then you use NLin fit to call the function and pass the parameters. So let me show you. Okay, the forward problem is what we just did. I showed you that, right? So OD45, function T-span Y0. Here's your function. Okay, it doesn't matter that I have 2 equations. You can have 10 equations, you can have 1 equation. Inverse problem. So then the inverse problem, how does it work? At the beginning, you have to guess your beta 0, beta 1 and beta 2. You have to put in guesses. Then you write your NLin fit, nonlinear fit, and you have to put in your x, your y observed, your function, your beta 0, and then over here is your output. So what happens is the NLin fit is going to call the forward problem 1 time to get started. And when it calls it the first time, it sends in the beta 0s. So the beta 0s, you see over here? Beta 0s come down and go into the forward problem. The function inverse is right there. So think about it. On the first time, the NLin fit tells the forward problem, I want you to run 1 time with beta 0 guesses. It runs 1 time through, and it gives 1 result for this function, and it sends it back to NLin fit. The NLin fit looks at the solution, and looks at the simulated solution from the beta 0s, compares it to the data, and gets a residual. Squares the residuals, gets that value, and then it adjusts, modifies the guesses. Modifies them from the beta 0 and it changes it to something else because it's looking for a better result. So then the NLin fit goes, it sends the new beta guesses back to the forward problem and generates 1 new solution. Solution goes back, so it takes the second solution, compares to the data, residuals, squares them, compares the residuals, the new residuals, the errors to the old errors, and hopefully it's coming down, and we're coming down to a minimum. And then it comes back and it adjusts the betas, and it keeps going like that. And what it's doing is it's adjusting the beta 1 and beta 2, and this is your sum of squares of errors. So the very first time you have, here's your beta 0 of guesses here and here. And it gets this value, sum of squares. Then it gives a new value. The new value might be here. Oh, it gets this one. Notice, this one is lower. We're trying to get lower sum of squares. Then it has a new value, like this. Comes up here. Oh, that's even better. And then another one, right? And like that. And it keeps going until finally it gets to the minimum. When it gets to the minimum, it compares the two. And when the tolerance is small enough, by like 10 to the minus 6, it stops and it says, okay, your results are beta 1 best fit and beta 2 best fit. And then it's finished. The inverse problem is finished. And now you've estimated your parameters. Does that make sense? Okay, that's what it's doing. So it's calling the forward problem many times until it minimizes the sum of squares. Okay, so that's how we set it up. Question? So he asks about, subtracts the two, gets the residuals, squares them, sums it up, gets one number. And that would be right here. Here's your initial guess and initial guess for beta 1 and beta 2. So you get this sum of squares. Okay, that's too big. So then the NLIN fit changes the beta values. It has a way to do that we can't discuss, but it has a way to change. So it changes the beta 1 to beta 2 over here. New values. Sends it to the forward function. Generates one solution, compares it to the data, gets the residuals, subtracts, gets the residuals, sums the square, gets one number, and it gets this. Well, this one's lower than this one. So it's moving towards a minimum. And then it keeps on doing that, changing the beta values, the parameter values, until it comes to a minimum. When it gets to the minimum, it stops. And so that minimum is right here. It means very sensitive. The parameters are very sensitive. So they're very accurate. But if it's very flat, then the parameter is not accurate. Now, you understand that it could be that, remember when I showed you yesterday, I turned it around and I looked at the beta, I looked at the X and then I looked at the Y, remember that yesterday? You could have a very steep X and a very blunt Y. So you could have this. Okay, let's see. K, right here, K ref. So that's Pascal seconds to the N. Pascal. Beta 2 is here. Inverse degrees C. Pascal. No units on N. Just make up a number. Okay. Okay. Let's just say he's 50, okay? 50. He says, oh, he's 50 kg. And I say to him, I'm 153. So I'm 153 pounds. How do you compare that? You convert my 153 to what? To kilos. So you have to convert to the same scale. Well, it turns out, I think that I'm 66. 153 converts to 66. Now you can say, okay, he's 60, I'm 66. You know that I weigh more, right? That's what you have to do with these. Otherwise, you cannot compare them. So that's what we're going to do. We have to get them to the same units. How do we do that? You multiply by the parameter. all the scaled sensitivity coefficients are Pascal. The sensitivity coefficients are not Pascal, but when you scale them, they become Pascals. Okay, if your eta is something else like concentration, milligrams per kilogram, then everything becomes milligrams per kilogram. Okay? So now I can make one plot. So in this case, we're doing shear rate on the axis. Most of the time I'm doing time, but in this case it's shear rate. So then I do... First I plot the eta. Then I plot the 3 scaled sensitivity coefficients. I can put them all on the same plot, and now I can look at them and say, okay, what's the largest one? It's obviously beta 1. So beta 1 will be the most accurate. And then I look at the other 2, and they're about the same size. And then I also say the shapes are all different, so I can estimate them. So this is how you compare the sizes. And you compare the sizes to the total eta. So if the eta is 100, and everything should be greater than, say, 10. If it's below 5%, you won't be able to estimate the parameters, okay? So that's my final point about scaled sensitivity coefficients, okay? All right. On what I showed you yesterday. So if you... Okay, so remember, I know, are you required to learn a foreign language? Or is it just English, or do you have to study another language? Just English? Do you have to study Spanish or Japanese or anything else? Nobody? Okay, so nobody's studying a foreign language? Yeah, that's because you already speak 3 or 4. Somebody speaks Malayalam and somebody speaks Bhojpuri and then English and Hindi. Yeah, okay. In the U.S., we have to study a foreign language. So at the beginning, when you're learning, it seems very difficult. But once you get started, it's not. You feel like, oh, it's very good. Okay. The purpose of doing this, going through all the lines, is so that you can use this, right? Because I use this code for all my research. When I'm analyzing data, I bring up this code and then I modify it for all my research, all my presentations, all my research papers, all my students who are doing this work. I use this code. So it's the same code every time, but of course you have to modify it according to what you need. Okay? So that's why I'm doing it. Okay, so you read in the data. Okay, so you see that. Read in the data, and then I just, okay, when I read in the data, I'll show you. Here's how you can work through it. So this afternoon we'll do it. So you do you see the run in advance? When you run, if you do run, it'll run through the whole code. So I'm doing cell by cell, paragraph by paragraph. If you want to do that, you just push run in advance, or you can just put run selection if you select it. So if I do run in advance, it goes there and it does the first one. Clears, and then it reads the data. Okay, so look at my data. My data have 2 columns. The first column is going to be the time. So I put that into the X. So X equals the first column. Right? This colon means all the rows. So all the rows, first column. Then Y observed is all the rows, second column. That's it. Okay, I have to put in guesses. So I put in Y0 equals 100, K equals 0.6. Those are my 2 guesses. Then I put them into beta 0. right? Beta 0, 1 is the first one. Beta 0, 2 is k. And by the way, if you want to see, I forgot to show you the model. So the model is right here. It's going to be exponential decay right here. dy dt equals minus ky. That's the model. Okay? Okay, then I define the function. So the function, I'm going to say f name equals at f, so first order differential. Okay, so let me do f order differential right here. Okay, and then I'll do this and then we're done for this. We'll go to tea break. Okay, so I put in y equals f order differential, beta t, this is what I taught you. First order model, differential form, and then I say t-span equals t. And then I have my name of my function, which is right here. Then I have t-span, and then I have beta 1, because beta 1 is the y0. So the beta 1, you have to put it right here as your y0. Then you write the function, and you say dy1 equals minus beta 2, because that's the k, times y. So the betas are here. Whoops. The betas are here and here. So when you do a differential equation, And I'll show you when you run this, everything will, you'll see everything come up. Okay, and then you can do it this afternoon. So let's show you. Okay, the next thing is we need to define the function, and I showed you the function. Right, so here's the function, differential function. And then now, okay, this will take a little bit of time. I'm going to show you how to compute the scaled sensitivity coefficient. So let's remind you how to do that. The way that you get the scaled sensitivity is you do the let me see if I can find it. Yeah, right. It's coming up. Okay, right. I have a picture here. So this line is this one. So you take your beta 1 and beta 2 guesses, and you just compute the function like we did. You solve the function. That's this one. And then you make a very small perturbation change on one parameter only. So we make a very small change here. Keep this one constant. Well, if you make a very small change, you'll have if you make a very small change in the parameter, you'll get a very small change in the solution to the function, like that. So now you have two functions. You just subtract the two. See there? You just subtract the two, like I showed you. Subtract, subtract, subtract. And then you divide by the bottom, denominator. And then that gives you the derivative, right? So then then you just plot this derivative for that one parameter. That's your sensitivity coefficient. And you get something like this, right? Right, because it's larger in the center than it is at the. You see, you see this one? This one's larger, this one's smaller, that one's smaller. That difference. So that's what you get. Does it make sense? We're just approximating the derivative. That's all we're doing. Okay? So that's what I'm doing now. That's the sensitivity coefficient. Sensitivity coefficient is just the derivative. That's all it is. It's just showing you how sensitive the model is to that parameter. So you have to do it for each parameter, and they'll all look different. But remember, we're scaling. So if you scale it, you have to multiply by the parameter. So you end up with just 0.001 in the denominator, and the beta 1 disappears because we want the scaled sensitivity coefficient. So I will show you in the code how you know when it's the scaled and when it's not the scaled, okay? Anyway, the code's for you to use, all right? So let me show you how to do it. Let me go back to the code. All right, so here is my scaled sensitivity coefficient code. So the first thing I do is right here. So this one, it doesn't matter, 500, 1,000. Okay, the scaled sensitivity coefficient is a forward problem because you are telling the code, fix the parameters to my guesses. So you fix the parameters, and that's a forward problem. We haven't done the inverse problem yet, where everything is preparation. So what I did is I spaced out my x values to 500. Actually, you could put in 1,000 if you want. Doesn't matter. There, I put in 1,000. It doesn't matter. You just have a lot. The reason you have a lot is you want a smooth curve. And it's a forward problem, so I can have as many x values as I want. When you do the inverse problem, you don't get to choose how many x values. It depends on your data. Whatever your data are, that's how many x values you have. But this is a forward problem, so I can have 10,000 x values if I want. Doesn't matter. Computer can do it. So you saw me change it. All right. So I just do a linear spacing on xs. I'm just giving a name so I can plot it. And then I go to my code, my SSC code, scaled sensitivity coefficient code. I give it the beta zeros, I give it the x values, and I give it the function name, first order differential. And now let's go look at the code. So I'm going to get, and this will all be posted for you. So SSC is right here. And this is how all my scaled sensitivity coefficient codes are written. In fact, the person who wrote in this one, my student helped me. I have a student from Bihar. I think there was somebody yesterday speaking at the student presentation, at the celebration. There was somebody, he was speaking, wasn't he from Bihar? He's from Bihar, right? So yeah. So he's speaking Bhojpuri. Yeah. So I learned a little Bhojpuri, Rahul Keshanbani. That's Bhojpuri. Okay. So anyway, my student from Bihar, he wrote this part for me, and he helped me with the code. So there's a lot of Indian input into the code. Okay. Joint venture between India and U.S. All right. So here it is with the scaled. I have SSC. You have to give the beta, the x, and the func. Okay? And all right, how does it work? Well, I have my D, which is my delta. The first thing I do is compute my Y prediction. That doesn't change. It stays the same. For all parameters, doesn't change. Then I made a figure because I want to plot it. And now I have my loop. Now my loop is because I have more than one parameter. So for the first parameter, it comes in and I have something, I say BE, I have beta IN. It's just going to be my differential beta. I reset it to the original betas. Then I compute my beta IN, and what I do is I just take beta and multiply 1.001. And then I get my Y hat. So my Y hat is this one. So that is the function with only one perturbed parameter. So what is that? So that's the other part, and now I just subtract the two. So to get the derivative right here, and so I do y hat minus y pred, and notice the y hat has an I because it's right now at the beginning it's doing the first parameter, just first parameter. And the reason I'm using a cell array with these curly brackets is the cell array allows me to put in as many points as I want. So if I have 1,000, it allows me to put 1,000 points into the cell array. The y pred, you don't need that because the y pred stays the same for every parameter, but the y hat changes for every parameter. Okay. All right. So then I divide. Now notice I divided by d. I did not divide by beta times d. If I divide by beta times d, then I'm doing the sensitivity coefficient. Since I want the scaled sensitivity coefficient, I divide by only 0.001. Okay? So you can look at my code and you know which one I'm doing just by looking at that. Okay, so then I save it. I call it YSenseF. I save it, and that's for beta 1. And then I plot it. Then I do the loop again, come back, and the I goes to 2. When it goes to 2, I reset my beta IN, and then I change beta IN because the beta IN starts with both betas as they are. Like this. Then I perturb beta 2. So right here, I perturb beta 2, right? Because I already perturbed beta 1 and I reset it. Now I perturb beta 2. I do the same thing. Y hat, I get everything else is the same, but it's computing the SSC for the second parameter. Okay, so that's the second parameter, and then I plot it. I plot it, and then I'm done because I have only 2 parameters in this case. But if I had 4, you just keep going, and it saves all of them. And since I have only 2 parameters, I put them right here. Y sense 1, Y sense 2, and then I do plotting. I do all the plotting here. Okay? So that's very simple program. That's it. All right? Okay, so now you'll see how it runs. Any questions on that? If you get too small, then there may not be enough change in the function. So it depends on your function. So if you do 10 to the minus 10, sometimes you end up with some rounding errors because it's computer code. So the computer code is only so accurate. So, and if you go too big, too large, then sometimes it becomes too rough. The estimate becomes too rough. But there is a range that you can do it. Based on experience. Yeah, so what you do is you can change it. If you're not sure if it's good, you can change it and then check it, and it should look the same for any choice. Yeah, trial and error, but you change the D and the plots should look the same. At some point they may change, but there should be a range of Ds that it works fine. It's just a numerical approximation. Yeah. Okay? Anything else? Okay, let's keep going then. So we'll do, go back to our code. Okay, that's scaled sensitivity coefficient. So so I'm plotting it before I do my inverse problem, right? So now that we've reached this point in the code, I want you to know that I've done everything that I showed you in my slides before running the code. So, as for example, let me show you here. Oh, I have to go back. Right here. So I've done one. I did the choice of the model, and I plotted the scale sensitivity coefficients. I know what my standard assumption should be, and then I chose my nonlinear parameter estimation method by using NLinFit. And then I chose my differential model, and later I'll change it to the explicit. So I've already done 1 through 5, right? And I'll show you the results. Then we'll do the inverse problem. So remember, most researchers, when I read the papers, when I go to the professional conferences, most people don't do in 1 through 5, they might do 1. They might choose the model and choose the solution method. So they might do 1 and 5. They don't know anything about scale sensitivity coefficients, so they're driving blind. They don't talk about standard statistical assumptions, so you don't know whether you're meeting those and how good your estimation method is. They don't really talk about the nonlinear parameter estimation method. Okay, so we do all of this before. Why? Because it makes your results much more useful, and it's a lot easier to get the results if you prepare very well. Just like it's better if you don't forget your GPS before you travel. I just traveled from Michigan to Canada, and I crossed the border, and I told my wife, I said, the GPS doesn't have any Canadian maps. So this happened 2 months ago, and it was too late. We were already driving. So we drove to Toronto, and she said, just drive in there, and then we'll try to figure it out. So I stopped and asked people at the gas station. There was an Indian guy running the gas station, another Arabic guy. They were very helpful. But we're wandering around Toronto for an hour until we finally got to our place because we didn't have the GPS. We didn't have a map, right? So that's a metaphor of what happens if you don't do these things. If your problem is really simple, you won't have an issue. But if your problem is difficult, it'll blow up on you because you didn't do these things that I just showed you. Okay? So now let's run it. Let's run the first part. Okay? So I'm going to move through it, and you'll see the scale sensitivity coefficients. I'm just going to do run in advance. Run in advance. So here we go. 1, 2, 3. Define the function. By the way, as I do this, you can see the workspace get bigger. Okay, then run in advance. Now it's going to do scaled sensitivity coefficients and plot them. You notice the curves are very smooth because I used 1,000 points. Okay, so the first one is for y0. That's this one. The second one is for k, which is the rate constant. So remember we talked about this yesterday? So are they correlated? Are the shapes the same? Uncorrelated, the shapes are not the same. If you divide one by the other, it's very different. These are very different, okay? So there's no the correlation is low. Which one is larger? The blue one, which is the y0, so that means the y0 will be lower error. The red one will have a higher the rate constant, which is typical. Okay, I'm ready to do my inverse problem. So let me show you how to do that. Here's NN fit. Okay, so I have my x observed right here. I have my y observed. I have my function, and I have my beta zeros. All right, and everything else I'm going to get a result. And then I just put out my betas. I compute my sum of squares. Sum of squares, you just take the residuals and you square them. Okay, so you do residuals transpose times residuals. And that's just, this is a transpose. This one right here, that's transpose. So you're taking a vector. The residual is a vector. So it comes out like this. So when you transpose it, you go like that. So what happens is you take this one times this one. You square this plus this squared plus this squared plus this like that. So when you do this resids, transpose times resids, that's what's happening. It's multiplying cell by cell and adding the sum of squares. Okay? So that's your sum of squares. Then I have my root mean squared error is the square root of the mean squared error. And then I will tell you the condition number. I didn't have time to get into it, but I can tell you that the condition number is automatically computed, and it's a statistical value, and you want it to be less than 1 million. When it gets above 1 million, it means that your estimation is becoming unstable. So you want to check that. And then you want to do your determinant of x transpose x. So that has to do with the sensitivity matrix. If one of the columns is proportional to another column, it will make this determinant become small. When the determinant gets closer to 0, your estimation is bad, and you probably have to fix one of the parameters. And that means that one of your scale sensitivity coefficients is going to have the same shape as another. So in our case, we won't have that problem, and I'll show it to you. Okay, so let me run this one, and then you see the result. Okay, so I got a beta of 102. My original guess was 100, and I think I guessed 0.5 for the other one. So I got 102 and 0.4. Okay, and then we have a root mean squared error of 4.8 out of 100. So it's about 5%. Not bad. Condition number is 241, which is very low. No, it's nowhere near 1 million. So that's good. Okay. Then we have determinant. Look at the determinant. It's 1 million. That's great because we want to avoid the determinant of x transpose x being close to 0. That's very bad. So these are excellent results. Of course, I made up the data, so that's why. Now, that's not enough. We need to find out what the errors are. So let me show you how to get the errors of your parameters. Because it doesn't mean anything to say my betas are 102 and 0.4. The question is, what's the error? Because what if the error on the 0.4, what if the error is 0.8? The parameter doesn't mean anything. Or if the 102 has an error of 150, it's no good. So we need to find out what the error is. So here's how you do that. Then we want to get the correlation matrix. So you put in core cov and you put in your covariance B, which came out of your NLin fit right here. There's the covariance B, and here's the here are the residuals, and here is the sensitivity matrix. So you put it in like this, and you get R and sigma. The R is the correlation matrix. What you want is the correlation between the parameters to be very low. The lower, the better. You want it to be far away from 1. If it's 0.98, that's bad. You want it to be 0.9 or lower. So I'll show you that. And then the sigma, I can put that in there. Standard error and the R. Yeah, I put that correlation matrix. Okay. Oh, I put it up on the top. All right, you already have it. Okay. So then I divide the sigma, which is your standard error, by the estimate beta. When you do the division, you end up with a fraction, which tells you the percentage error. Okay, we'll look at that. And then they have a special command for confidence and prediction intervals. So that's your prediction. That's your predicted line. You can have confidence intervals around it. The confidence intervals, 95% confidence intervals tells you where you would expect to have 95% of the regression lines to fall inside that. Then you can have prediction intervals. Those are bigger because let me do this. This is 95% prediction interval or prediction band. The reason those are larger is that's where you would expect to find 95% of the data. So you can put both of them on there, and I'll show you how I do it. So the first line is for the confidence interval or confidence band. When you put a lot of them together, it's a band. So you put in your Y prediction, I'm sorry, that's what you get, your output. You use nonlinear prediction confidence interval, and if you want to do the confidence interval, I put it here, confidence band for regression line, right here you put curve. Curve meaning it's for the curve. If you want to get the prediction interval, then you type in observation because it's the data. And that is the prediction band for the individual points. So that's what I put in. And I get out delta, and I get delta observation. So then I calculate the Y span, which is just the range of Y. And I get my relative root mean squared error. I take the root mean squared error, I divide by the total Y span. We hope that that is under 10%. If it's 20%, that's getting a little bit big. And then I I make my confidence intervals, I take my Y prediction and I add the delta and subtract the delta. For my prediction intervals, I take my Y prediction, I add the delta observation, and I subtract the delta observation. So now I have my confidence band and my prediction band. Okay, and I'll show you. I'll run all of this. Okay, and now I want to plot my output. So the output is going to be Y prediction and Y observed. So by the way, these are handles. This H1, when you put H1 of 1, it's a handle. So H means handle, and you can connect the handle to the legend. I'll show you how to do that. So anytime you want a legend, just put H1 on the left side, or H2, H3, H4, and the legend will give you 1, 2, 3, 4. I'll show it to you. So the first thing is, I plot my X versus my prediction line. And you know what? I should change that. It shouldn't be X, it should be so few points. I like doing a lot of points to make it smooth. But let's see if I can find. Let me just do a quick check. Oh, I got it from there. Okay. Well, let's not worry about it for now because time, okay? It's still correct. It's just, it would be smoother if I did it differently. That's all right. So let's keep it. And that would be my predicted line. And then we do my observation. So Y observation. And that will be, so I have to say, on the first one, I do a line. So I say the line width and I make it thick. So I put a 3. For the observation, you have to tell MATLAB, do you want a square? Do you want a circle? Do you want a diamond? So I put square. I put the marker face color because filled marker. If you don't put the marker face color, it's just a circle. If you put the face color, it's a filled circle. So it's easier to see. And then I put my labels in my grid. So that's the output of the line. That's just the line and the data. So predicted line and the data. Now we do the confidence bands and the prediction bands. So you notice I haven't done the legend yet. Okay. So I have H1, 1, 2, and then I have 3, H1 of 3. So you plot the X and you plot the upper confidence band, and then I do X and plot the lower confidence band. The reason I didn't put an H1 on this one is I don't want a legend for the upper and another legend for the lower. I just want one legend for the upper and lower. And then I did the same thing for prediction right here. And you notice I use a dash dash because I want a dashed line. And I made this green and I made this one red. So G and R, green, red. Now I can do my legend. Okay, so the legend is looking for four different parts. So the parts are, the first one is the Y pred, right here, Y pred. So that's right here, Y pred. The second one is Y observed, right here, H2, right, H1 of 2. And the third and the fourth are the CB, confidence band, and prediction band. So those are your 4 legends that correspond to the H1 from 1 through 4. Okay. All right, that will give me my output, and I think I did a hold on. Yeah, I put a figure, and then I want everything I just talked about on one figure. Therefore, I put hold on right here. So the hold on means it will put everything on until I stop. Until the next time I say figure. So now I start a new figure for residual. So my new figure is residual, and I put figure, then I do hold on, and then I plot X, and I plot all my residuals in a scatter plot. The Y line and the X line, all I'm doing is putting a line at 0 so you can see it, the residuals back and forth on the 0 line. And then everything else is just plotting. Okay, that's nothing special there. Okay, and then I calculate the number of runs. The number of runs means how many times do the residuals jump over the 0 line. So the here 1, 2, 3, 4, 5, 6, like that. So we want to have about half. If there are 100 data, we want to have 50 runs. Okay. So all I did was I took my crossing. So I took this one here, the residuals. So notice I did the residuals from 2 to n, and then I did from 1 to n minus 1. So what I'm doing is, if you have these residuals, and I'm offsetting by 1, I'm comparing each residual to the one in front of it. Okay, and then I take those two and I multiply them by each other. If the sign is negative, it's a run. If the sign is positive, it's not a run, because if it's negative, it means it jumped over the 0. So then I just do my sign. I get the sign. And I do here, if residual sign is less than 0, then I count that as a run. That's it, and I just add it up. So then I put number of runs equals, and then this one right here is just telling you how many digits you want, and then I say count how many. And then I put in the minimum number of runs is n plus 1 divided by 2, and I put that as well. So that tells me how many runs, because I need to do my residual analysis and check my standard statistical assumptions. And then I do a residual histogram because I need to see if the residuals are normal, Gaussian, okay? So there's a special command in MATLAB where you can do histogram. You just do your residuals, and then the 10 is the number of bins. The bins inside of a histogram. You can separate it. So usually 10 is enough. And then I just plot that, and then take a look at it, and then see if it's close to Gaussian. And the last thing I do is I replot my scaled sensitivity coefficients, but I plot them based on the estimated betas. Notice this one is beta, but the one that I did at the beginning should have been beta 0, right here. See that? Those are the guesses. So if the guesses were good, then the SSCs, the scaled sensitivity coefficients, they should look approximately the same. If my guesses were not that good, then you'll see a difference. But I need to have good scaled sensitivity coefficients in order to get good parameter estimates. Okay, so now you've already seen everything up to, not including the inverse problem. So let's run after that. So let's run the confidence interval. I'll start right here. So I open my ribbon, and I will run in advance, and you'll see the confidence interval. There are the confidence intervals, right? So 98 to 105 is for the first parameter. 0.3 to 0.42 is for the second. And by the way, these confidence intervals, if you look at your statistics book, typically they are double the standard error. So if you look at the standard error, which is coming up, I'll do that now. Here's the standard error. So the standard error was 1.9. And okay, so 1.9 times 2 is 3.8. So it should be 3.8 plus the beta. Okay, so let's see. Here's the beta. Okay, so the beta was 102.2. 3.8, so that would be, did I say 3, wait, 1 point, did I say 3.8? I think it's 3.8. So that would be 106. Yeah, right here, 106, right? I just added the 3.8. And then you subtract 3.8 on the other side. That's how the confidence intervals are computed. You double the standard error, and you add and subtract from the beta. Okay, here's the correlation matrix. So the correlation matrix works like this. Error. The second one had a 2.6. Do you remember when we looked at the scaled sensitivities? Isn't that what we said? The scaled sensitivity coefficients told us that the first parameter, the y0, would be lower error. So that's what you got, right? And you should always check your scaled sensitivities. They will tell you that. Go, sit down. But that's not, this is just the beginning, right? We need to put confidence intervals. We need to take a look at those. We need to look at all the standard statistical assumptions, okay? So let's keep going. Okay, there are my confidence intervals. So I have my confidence intervals are very tight, and then I have my prediction intervals, which are larger. So you can see that the data, here's one data point and data. But I want to check to make sure what is the actual nuns to make sure that they're uncorrelated. They look uncorrelated. By the way, here I got my relative errors. Okay, my y-span was total 100. My relative root mean squared error was about 5%. You can see, right? Not bad at all. So you do have normal errors, Gaussian errors. And then I think that's it except for the scaled. Okay, this is my final scaled sensitivity coefficients based on the estimated betas. So that's pretty good. I mean, that tells us we're doing. In fact, I haven't even looked at this for 6 months, this tool. But it's so simple, I can just go in and remember. Okay, you just go data. Find resids. Comes up automatically, and it automatically chooses a number of bins. You can change that if you want. Create data set. If you want to change the bins, you can do that. I don't really care about that. I think it's good enough. Select data. Hold on. It is new fit. That's what I was looking for. Okay, so now I do the fit. Look down here. The mean of the residuals is 0.3. Well, the scale is 100, so that's pretty close to 0. And print to a figure. And then you can put that in your research. The other one is fine, and it depends what you want. The other one that I have is the one that you saw, which is this. Whoops. So the first one is a differential model, right? dy dt equals minus ky. If you integrate that, you just get an exponential decay. y0 equals e to the minus kt. It's the same model. But the first one is differential. The second one is explicit. So I can do that in 1 minute. Watch. Because I already have it set up. So let me bring it up. Let's bring up, well, let's go to my code so you can see it. I'm going to run the same thing, and you'll see we get the same answers. So if you go back to my code, and you find that right here, do you see this? I have a choice. So I'm going to change it, and change it to first order explicit. Right here. Here it is, first order explicit, beta t, and you notice there's no ODE 45 because it's not a differential equation. It's already been integrated. So now I have y equals beta 1 times exponent minus beta 2 times t. It's the same model. Same parameters. But we're doing it with an explicit equation instead of a differential. Is everybody with me on that? So all I did was change this one, right? Everything else is the same. So let's run it. I'm going to run the whole thing. Run. Figure 1, figure 2, looks the same, right? Figure 3, looks the same. Figure 4, same. And then figure 5. Same results. Because it's the same model, but it's done in a different way, okay? Okay, so you can use this. I can't remember if I posted it. I'll make sure it's posted. Do you know if it's posted? I can't remember. I'll post this on the Google Drive. Okay? Post on the Google Drive. So it looks like we're at the end of this class. I do have another code which is based on this code, and it's for the rheological data. So what I'm going to do is I'll look at that, make sure everything's fine, and I'll post that. And what we can do this afternoon at the computer lab, you can go ahead and start with the remember I showed you the curve fit tool. Okay, here's the CF tool. So you can pop the CF tool open and then watch. All I just do my X data, right? So I need this. Okay, custom equation. Yeah, it's easy. Don't worry. I mean, it's not. Let's get rid of that. And let's just write in our equation. So our equation is going to be a times exponent minus b times x. Okay, so there, custom equation. And then just get your data. So your data are x. Right here, x, and y. Is y? Oh, y observed. I changed the model. Oh, okay. You can do exponential. Yeah, there it is. They have exponential. So the b for them, the b will be negative, right? It's the same model that I was using, right? Now remember, in the CF tool, you cannot do differential. You have to do explicit. That's okay. So I chose the a times a exponent bx. Well, let's look at let's see what the results are. 102.2. You see the confidence intervals? And minus 0.4. It has to be minus, right? Minus 0.4. I think that's what we got, right? Yeah, there it is. Right? So that's what we got, 102 and 0.406. I'm getting confused, too many. Hang on a second. Dual plots, they have a contour plot and prediction bounds. 95%, so see, they can put them on as well, which is what we did. And so they got the same results, but you can't see scaled sensitivity coefficients, right? It's limited in what it can do. And the other one was residual plot. So here's the residual plot down there. Their plot looks a little different from mine. And I'd have to make it bigger, but let's see. They do it a little bit differently. I just put the points on. They put the arrow. They have a line on it, okay? So you can do it the same way, but you have to use the explicit form. So I think this afternoon what we'll start with will be the one I showed you before. The one I showed you before was, you remember when I showed you the surface? So you can start with the surface and then run it on the CFIT tool, and you can also run the code, okay? You can start on that. I'll help you with that at the session in the afternoon. And then you can try this one. And then if I have the rheological data, I'll also give you that one as well. So you can try different ones. You can try CFIT tool, and you can run the code. Then you can take it and use it for your research. Okay? Questions? Was that helpful? Okay, hope that helps you in your research, all right? So then I'll see you at 2:30, I think he said. 2:30 over at the computer lab. I think Dr. Sogi will confirm with you, okay? Great. All right. Have a good lunch.